ETH Zurich, where he's a professor of computer science, right?
Yep.
He's also very, very involved with various projects at Microsoft, including chip design, to my understanding. So, invest in his whatever he tells you to invest in, and you'll become rich, maybe. And Thorsten's lab has been involved in a lot of different interesting issues having to do with high-performance computing and AI, ranging from things like data compression to AI tasks somewhat similar to the ones that we do in our climate modeling group. So it was great that he just happened to be coming here and was volunteered to give a talk to us, and we're really happy to have him.
Thank you so much, Chris. I mean, I'm actually super glad to be here. I'm sorry I couldn't make it last time. A year ago, I had a talk scheduled, but then United canceled my flight, and it was a problem. I couldn't make it, but I'm glad it works this time. So yeah, as Chris just said, I'm actually here quite often. I'm spending my summers in Seattle every year since about 8 years now. And this is an AI, this picture is an AI-generated picture that kind of talks a little bit about the problems that we could be having. What are the problems that we could be having? Actually, I'm sure you've been here last year. So last year was quite bad. I'm sure you've been here about 6 years ago, where it was even worse. And the reason why it was worse, you of course know. So it's a bit of a sad thing that Canada is on fire pretty regularly. And it was one of my most interesting experiences was when I was here, as I said, about 6 years ago, 2019. When it was raining ash. The first time of my life I've seen ash raining down, and when the bus driver tells you stay safe when you leave the bus, when it's a sign that something is maybe not in order. And so you can see in the statistics here, if you look at the tree cover loss in Canada over the last couple of years, so 24 is not on that yet, but 23 was pretty bad. One of the worst years. And in fact, 23, Canada lost 15 million hectares, which is 27% of the global tree cover loss just due to wildfires. And we all know what the reason for this is. The reason is that this area of the planet is actually excessively warming compared to other areas of the planet. If you look at the map, if you look at the northern areas, this is a relative heat difference to the previous years. On average, you can see the north is pretty heavily affected, so we want to understand what's going on. I mean, I'm preaching to the choir here, and I don't want to go into more motivation. But one of the questions is, how do we actually not just look at this in the past, because the video I just showed is the past view, is what happened over the last couple of decades, but how do we look into the future? And since I'm a technologist, I want to defer to another technologist. This is Jensen Huang, probably one of the most successful entrepreneurs you could argue, but in the technology space, a quite successful entrepreneur, having a company that used to be the largest company on the planet in terms of market capitalization for a week, before it was passed, and now it's way down, unfortunately. But what he said, and he has an interest in climate, quite a vested interest. I've been on several calls with him on this specific topic, but what he said is the climate simulation is basically impossible today. Of course, now you all disagree because you say, well, we have simulation results, we talk about this average global warming, and then we look into the future. But what he really means is that, yeah, predicting the average temperature is okay, we can talk about that. What we don't know is how it affects certain regions on the planet. And that we should all relate to. It's very hard to predict what happens in a certain region 40 years in the future, or 100 years in the future. So, and the question is now, why is this the case? Why is this so hard? Why can we not just go forward? We have all these magic computers. They train AI models bigger than we've ever seen. Why can we not actually train, or why can we not actually do climate simulations in a way that are high fidelity and at a local scale? So let me go a little more into detail. And so you could now say climate prediction is extremely demanding, or you could use the word impossible. Well, impossible means today. Now I want to outline the workload that we need to solve in order to solve a decade-long climate prediction, which is basically a decade-long weather forecast, but it's a sampled weather forecast. We forecast multiple different weather scenarios. So the first problem is we need to pick a resolution. We need to discretize the Earth, and we need to understand what the fidelity of the discretization of the representation of the Earth in the model is. You can imagine this as like a JPEG picture. How many pixels do you have to resolve the thing? If you have a megapixel of a room like this, it would look good. if I give you 1,000 pixels, a kilopixel, you would not get a very good resolution, very good representation of the room. It's very similar here. And what we look at here is the grid spacing, the space between two grid points, between two pixels that we use to represent the Earth. On the very right, we have 100-meter grid spacing. On the very left, we have 1,000 kilometers grid spacing. Okay, so that's, now we are talking about computational effort. But one physical property is this, and most of you know this, as we increase the resolution of the grid, we actually resolve more and more processes. What the process now, these are phenomena that mandate our weather and our climate in the future. For example, clouds, turbulent phenomena, big movements in the atmosphere, and things like this. So the problem with this is we can never resolve all phenomena. So because it's a chaotic equation, we are solving Navier-Stokes equations or Eulerian equations. They're all of chaotic nature, which means an arbitrarily small change in the starting condition can create an arbitrarily large change sometime in the future. So this means at any point, like, we have to cut off this resolution. But the more we resolve, the better, the more physical principles we get. So if we now cut it off at 100 kilometers, we basically only cover continental scale effects. Right? So there are not many continental scale effects. Actually, my climate friends tell me there is not too much. By the way, I'm a computer scientist. I have dangerous half knowledge in climate science. So you're the climate scientist. You know this much better. Please correct me if I'm wrong with anything.
This is why Chris Brotherton is chuckling behind you.
Exactly.
Yeah, keep looking the other way, Torsten.
Exactly. I'm like, oh no. So then if you go to 25 kilometers, my climate scientist friends tell me that you can resolve cyclones and very large effects. And if you go to 1 kilometer resolution, apparently you can resolve storms. Clouds, you can only resolve at about 100 meters or smaller, because there are small clouds, very small clouds in parts of the planet. Okay, so that's now nice. So ideally, we want to run in 100-meter resolution, right? So they're actually even finer, maybe 10-meter resolution. So there are people who run climate and other simulations at that resolution, but for very small areas. So for example, the country of Singapore is doing that, or the city-state of Singapore is doing that. So now, what is this red line? This red line is the resolution we run the weather forecast today in Switzerland. So partially responsible for this is an ex-colleague of yours and a friend of mine, Uli Forer, who's been working on this, and he's at Meteo Swiss, our federal office of meteorology. So that's the resolution we run for this little country. So let's now take an excerpt of this little country and let's zoom a little bit in. And this is now actually a visualization of what we can do with that simulation. So you see the resolution here. And this is faithful. Well, it's not too great, the frame rate, but believe me, it's full frame rate on my laptop. It's actually a faithful visualization. So all pixels you're seeing here are actually pixels, original pixels in the simulation. So the only problem is that this is about 77,000 square kilometers that we are simulating here. We can simulate this at high enough resolution that you can observe clouds forming, you can observe like smallish scale effects. This is absolutely perfect. The only problem is the Earth is 510 million square kilometers. So it's much, much, much larger. So we're looking at about 0.015% of the total, or 1/6,000th of the Earth here. So we can do it. Like we have a code that runs it. We could do it. We just don't have the compute performance to do it, because this is running on a sizable machine and it's already quite expensive to do so. So now another thing that we would consider is the amount of storage we would need in order to store the output of such a simulation. Because of course, what you want is you want to analyze the data. You want to understand what's going on after you ran the simulation. Otherwise, you wouldn't need the simulation. So now if you look at a single trajectory and record a significant number of reasonable time stepping and a significant number of variables, this depends on the simulation itself. On the left side, you have about 500 megabytes sitting on my USB stick. On the right side, you have about 50 petabyte where you need a significant size data center to do this. So also a problem. Actually, you can see this is scaling really badly. I mean, this is scaling cubically with the resolution, right? Because you need more and more points. The other point is I mentioned, well, I just showed you a weather forecasting scenario. What we're actually doing for climate is we are running multiple weather forecasting scenarios, because we don't predict a specific weather event in the future, but we predict the distribution of weather events into the future. So we need to sample that distribution with sufficient accuracy, which means we need to run, I mean, there are many ways to do this, but the common way of doing this is to run an ensemble model. You run multiple different ensembles, and then you derive the distribution from it. So on the y-axis, you now see multiple ensembles. The single simulation is there, so 10 to the 0 is a single ensemble. Now, what you can do actually on your laptop on a machine like this, you can run continental resolving climate simulations at the single-digit ensembles in a reasonable time. Right? So that's possible. This is why most of the papers in this area are actually in this area. What's even more shocking when you go to things like CMIP6 and high-resolution simulations, what they mean by high resolution is like 25 kilometers or something, which is quite still pretty bad in terms of resolving things. So now we could say we add more compute power to this. So compute power could get us one of two things. We could either get a higher resolution, or we could get more ensemble members, right, at the same budget. Because at the left side here, what I'm showing, we want to operate. This is a prediction of the compute time needed for one simulated year per day. So in about 1 month, you can run a 30-year campaign, right? So now we could draw real computers on this in this diagram. We could say, well, the Levante system, it would get us. This is a system in Germany that's exclusively used for climate research. That's one of the largest ones exclusively used for climate research that I know. It's actually the largest one. You can get a 5-kilometer resolution at 1 simulated year per day for a single ensemble. And then, of course, you can get more ensembles, but that would reduce the resolution you would be getting if you want to stick to the 1 simulated year per day. Now, you could look at the LUMI system, which is the largest supercomputer in Europe that we have right now. So that's great. That gets you more. Then you could look at the Frontier system. That has not been benchmarked yet, but we are on it. And that's there. So Frontier gets us 1.5 kilometer, 1 simulated year per day. So, yeah, 1 simulated year per day. And the problem is we cannot get outside of this. Right? So if you want to go there, either more ensembles or higher resolution at that performance, we don't get it. And that's a bit of a problem. So we actually had a meeting about 2 years ago, and many of you have probably been there in Berlin, the EVE meeting, the Earth Virtualization Engines meeting, where we decided or discussed in the climate community, what would we need in order to have a good prediction at local resolution, but at global scale? So meaning that I can predict what the weather over Seattle is going to be in expectation in 50 years, but specifically over Seattle, not just the average temperature, right? That's the big thing. And we wrote an article on this. This figure comes from that article. Unfortunately, that thing here is what the climate scientists decided we would need, which we don't have. So now the question is, how do we achieve this? And this is where people like I come in as a computer scientist. Well, we could play tricks. We could build faster supercomputers like we've been doing the last 40 years. We were facing one problem with that, because the last 40 years we've been relying on what's called Moore's law and Dennard scaling. These are two effects that drove the semiconductor industry for 40 years. So Moore's law is a law that says that about every 18 months, the number of transistors doubles basically for free. Okay, that is not going on in that respect anymore. The number of transistors still increases, but it doesn't quite double. Right? So it has slowed down. You could argue that Moore's law is kind of still alive, but has slowed down. Some people say Moore's law was bound to these constants. These constants are not met anymore. So some people say it's dead. Some people say it's alive. But it is. We're still growing, not at that rate that we used to be growing. Dennard scaling ended more than 10 years ago. Dennard scaling was the scaling where we basically said, when we shrink the feature size of a transistor, the proportional energy consumption of that transistor would shrink with that feature size, right? And that ended a long time ago. So now we will not, and that's not nice, because if we were shrinking it, we got more transistors for free, and they used less energy. So we could actually cool them nicely. That stopped, and we couldn't cool them anymore, so we couldn't increase the frequency. So this is the beginning of the multi-core era, the beginning of the massive parallel era, the beginning of the GPU era that is now 10 years in the past. So both of these laws that were driving semiconductor industry are in trouble. So they're not driving the semiconductor industry as they used to. So this is going to be hard, the faster supercomputers. We basically need to say we need more capital investment to build larger machines. At the end, we can build very large machines. It's a capital investment question. How much are we willing to spend? And now in the political climate, I'm not sure if there's too much money here for climate, but we will see. So we have another trick. We could cheat with machine learning, and this is where you come in. Right? So we could cheat with machine learning, and so there are multiple of these things. But let me go a little bit forward. What do we actually need in order to drive these long climate predictions? I don't want to call it simulations, because much of that will be emulation to some extent. So we have a whole chain that is used today. So we have data, compute, and models. Right? And these are different things in different contexts. So we have observation data, we have simulation data, we have various accelerated compute forms these days. And models, we could have either AI models or simulations. Right? So these, in my terminology, are both kind of models. Some use more flop and more computation, others use less. And then we have this workflow of climate scientists where we have observational data, weather and climate simulation. that produces simulation data, and this could also be emulation or AI models. And then it produces some climate insight. I want to talk about the first 3 elements in this, how we can use tricks, specific tricks, to optimize each of those elements. These were tricks that I developed in my research group together with collaborators, many collaborators actually, and I would love to collaborate with you guys in the future if the opportunity is there. So let me start with observation data. So the problem with any simulation is that we need a starting condition, and so we need to take the very unstructured, very sparse sensor data we have on the planet and integrate it into a dense grid that we can start the simulation from. This process is called assimilation. I'm sure many of you are familiar with this. So we basically take satellite data, we take sensor data, we take all the data we have and assimilate it into a grid where every single number, every single grid cell has a specific number to start the simulation from. Each of these numbers has a different certainty. If you have a sensor sitting right next to the grid cell, you have a very high certainty. If you have the sensor 1,000 miles, the next sensor 1,000 miles away, then you have very low certainty. But we still have models to do this. By the way, all of the imagery here is AI generated. You can see there's not quite the nicest grid here, but this is part of the pun of this game, of this talk. So every image you see is AI generated and will have some minor flaws. So what do? Actually, we had an idea a long time ago, like nearly 5 years ago, that we could use diffusion models for the assimilation process. And I think it's a pretty powerful idea. So I want to run it by you. Many of you probably know, but let me summarize in 2 minutes how a diffusion model really works. It's a very fascinating model. So you basically start from an image and you add noise to it in steps. Like random Gaussian noise with different forms of noise you can add. It doesn't really matter that much. So you'll basically take a discrete distribution that the image is in to kind of a random distribution, because if you add enough random noise, it'll be completely random at some point. Okay, what do you do then? Well, that doesn't help you to add random noise to images, you're just noising it. But what you do is every step you add noise, you learn the inverse function. You train a neural network that takes the noisy data and that produces the less noisy image. It's very easy to do this because you've just added the data. You have the training example and you have the input, right? So you can just do this with enough compute. You can do this, and then at the end, what you have is you have a network that allows you to take all noise and generate an image. Of course, people do this with some form of bias because they want to generate a specific image and not just a random image. You can do this with random images as well, but it's not very useful. And this is how all these image generation models work. Like Google's ImageGen, DALL-E 2 was a model like this, and Stable Diffusion, and many models like this. So this is great. But what else can you do with those? What's quite funny, as you can do with those, is you can now say, well, I have an image, and I want to replace this dog with a yellow cat. Okay. What you can do then is you can create a mask for the dog. And so you tell the model that all the pixels that are black in this mask, they must end up like the original image. So you bias it towards that. But all the pixels that are in the white part, they must generate the yellow cat. Okay? So that's called inpainting. And this inpainting is quite nice because you can actually use the same idea to inpaint the missing points that you don't have observations for into your grid. Like this is the fundamental observation that we made. So you could do this, and at the end is all details. I mean, so this is how it looks in an image. You start from a random image, and you force the pixels to end up like the original image in the black mask pieces, and then the other ones go into to the most likely statistical outcome with the specific bias of the yellow cat. So we do exactly the same thing, but what we do is that all the black masked pieces are now the observation data. And we ask the model to fill in all the missing pieces that we don't have observation data for. And this is the assimilation process. So we have a paper on this. We call it DiffDA, diffusion-based assimilation. I can go a little bit into detail, but I don't want to spend too much time because it's kind of really standard diffusion model. So we basically use a GraphCast network to implement the diffusion model, where you need to train a model that learns how to denoise. We just use GraphCast. You can use any model for this. It doesn't really matter. And then we have 2 innovations in there, which are quite nice. And again, I don't want to go into too much of the detail. There's a full YouTube talk online if you wonder how it works in detail. It's a 30-minute talk. I want to tell you about many more tricks, so this is why I'm keeping this very short. But I want to emphasize the 2 innovations. One is actually what we call soft masking, where for numerical reasons, you don't use a hard mask, but you use a Gaussian blurred mask. So every point where you have a measurement result, the intuition is that if I'm measuring the temperature here of 30 Celsius, it's in a 1 kilometer surrounding diameter, it's not going to be 5 degrees suddenly. So there's a smooth temperature curve. So we do that. We take the measurement points, which are point measurements. They're actually subgrid measurements because they measure in the meter resolution, and the grid is a kilometer or so. And we extend them with a soft mask. Right? This is obvious, and we use specific kernels for this, like the soft bleed kernel. But these are all technical details that you can look up, and that improved the performance quite a bit to get to real assimilated cases. So now we could look at the results. I mean, it's we basically at the bottom we take sparse observations here. So these are point observations. You don't even see them on the screen because they're single pixels. Then we do the soft masking on it. Then you suddenly see them because they get broader. And then you could say, well, we could compare a GraphCast forecast just without the bias of the additional measurements to our diffusion assimilation. You see that you see no difference on the screen. Of course, it's much better if you look at the arrows, like the difference between the true thing and the predicted thing. What is the truth here? The truth is error 5 in this case, but it doesn't matter too much. And now you see that if you just use GraphCast, there are lots of arrows up here, like the red elements. The more red and the more blue, the worse. Red is too warm, blue is too cold. If you just do interpolation, it's also not so great. So you have some problems. And if you do diff-DA, you actually get a quite nicer distribution. So just believe us, this method is working well. You can try it yourself. You can reproduce it. It's actually quite nice. So we were talking to ECMWF right now. They're looking at adopting similar techniques. So this is great. So this is one trick. Use diffusion for assimilation. It's quite a nice trick. It's an established machine learning thing. So now let's go to the next piece. Now we have the assimilation solved. We took all the observation data and we gridded them into a nice simulation model. So now let's see how to simulate. Well, I mean, all these recent or not so recent, I mean, 23 in the AI space is like ages ago, but models that claim to be doing as good as simulations, right? There's GraphCast, there's Pangu Weather, there's ForecastNet, and even IBM in 24 came out with what they call Priti, I think, Prithvi. So every major company and every major organization has their own weather prediction model. It's not a climate prediction model, it's a weather prediction model because they work on weather timeframes. And now you could argue, well, you replace that whole simulation stuff with AI, who cares anyway? This is going to work. The benefit of this is that actually these models are typically a factor of 1,000 cheaper than running the simulation at reasonable scale, at planetary scale, at reasonable resolution on planetary scale. So a factor of 1,000 is a lot, right? You're basically condensing your big supercomputer into a single GPU system. And that's great. And the other benefit of this is that actually you could claim that these simulations are learning from data. So they have a much better adoption to local effects that are happening on the Earth, because they actually may learn a different diffusion kernel, different PDE over the oceans, over the land, over specific localities that have specific effects, like the Himalayas on Earth, which weather and climate models are very often manually modeling, where there are very often worse approximations to reality than an AI model could in theory learn. So these are two potential benefits, but now they have one problem, because they have the problem of out of distribution things happen. And in AI, the problem is you garbage in, garbage out. You really only know, the model can only know what it has seen in the data up to some certain interpolation range, but it's really bad at extrapolation. And so because there are good reasons for this, it usually does a linear extrapolation, which is good in some range, but if you go too far out of distribution, it's going to be really bad. So you want to stay within your distribution of things you have observed. So several scientists actually put this to the test. They took these models and they looked at them for weather forecasting after the training time ended of these models. So they looked at specific extreme events like the storm Ciaran that happened in November 23, which was after these models have been trained. And they looked at how well would these three models, GraphCastNet, Pangu Weather, and ForecastNet, actually predict the storm. Okay, well, let's see. This is the paper. It's not our paper. It's very esteemed authors from another institution. And they also compared it to ECMWF's prediction, okay, which is like the golden truth. That's what in the US is often called the European model when it comes to hurricanes and things like this. They're often the best model. Okay, now let's look at this. So what happened? Well, the error 5 reanalysis is actually the real like ground truth, because that is after the fact. They have used all the observation data and re-assimilated it into the data itself. So all of these forecasts look at 48 hours in advance. So there's the event at time t. There was a recorded wind of 122 kilometers per hour. It's pretty massive. And we look at the models 48 hours before. That's the information they get, and they shall predict this event. Okay. So if you do this with the IFS simulation, you get a result of 129 kilometers per hour. We just look at the maximum wind speed here. That's just the single metric we're diving in. Okay, GraphCastNet actually is a much shallower wind speed, 93 kilometers per hour. Pangu Weather 90, ForecastNet 93, and ForecastNet V2 90. So that is a significant difference between the simulation, the reality, and these predicted models. And unfortunately, if you look at the country of Germany, they would only issue a severe storm warning after 100 kilometers per hour. So none of the AI models would have triggered a severe storm warning, as if you've paid attention, there were multiple fatalities in that storm, and probably many more have been prevented by issuing a storm warning that had a storm warning. So there's a certain danger to these models. The interesting thing is here, quoting from this paper, so the forecast itself before was nearly indistinguishable between the models and the real simulation. Only the damaging winds were not really covered. So this is a typical example of an extreme event not being covered in these models. So something that people should look into, and there's actually another group who looked into the reasons for this. Why is the wind a problem? So there's another paper that did another study on a very similar setting, but now over Southeast Asia. It's the Typhoon Doksuri. So that happened in July 23. More fatalities, unfortunately, and was the strongest in the region in 23. So bad. Again, different author from the ECMWF, but they looked a little bit more in detail. What they looked at is the vertical wind component. So all of these AI models, they're trained on horizontal wind, UV direction. Okay? None of those is trained on the vertical. But now, as you know, if you have a basic physics understanding, if I do this here, if I'm just compressing air, there is a vertical component forming automatically. It's going up and down, right? So in reality, if you have a mass conservation law in your physics equations, that is covered. Like the simulation will faithfully simulate that vertical wind component. By the way, vertical winds are huge problem for some people. Like I'm working with the climate center in Singapore. They have a huge problem with vertical winds because they stack in the port, they stack their containers very high, and the vertical wind can topple these containers, big damage. Okay, so now if you look at the ground truth, again, this is the vertical wind now. It's interesting. If you look at the ECMWF IFS, that looks reasonable. And now if you look at an AI model, that's completely unreasonable. So the AI model's vertical wind prediction is extremely bad. But why is this extremely bad? It's never been trained for it. It is something it would need to learn implicitly, but it doesn't, because there is no oversight. There was no training to predict vertical wind. And this is another thing. So how do we make sure that we train these AI models with all the right features that we need to use them later? This is just a warning. There's another obvious thing. If you look at global warming, if you look at climate timescales, not at weather forecasting, things change. So there's a fixed bias in the data, essentially. This is very simple. If you look at the observed temperature in the 1900s versus the observed temperature in the 2000s, that is much higher because there's warming going on. So now, if you look at this again, and we look at the forecast bias for 2-meter temperature in these models, that's an interesting one. So if you take these 3 models, GraphCast, Pangu Weather, and AIFS is now the ECMWF's newer version of the model. If you set a starting condition in 1955, that is in 1955, then some of these models, like GraphCast and AIFS, they would get a positive bias. So this is basically the mean bias of how much too warm they predict the future. Right? Weirdly enough, Pangu Weather has a negative bias, but that's kind of strange. Generally in Pangu, if you now set the starting conditions for a forecast in the 2020s, with the 2020s, you get a reasonably accurate non-biased prediction. Okay, that's not bad. But if you now look at expected warming for 20 years from now, or actually 30 years from now, no, 20 years from now, they will develop a cold bias. So these models that are trained on a fixed time data, they will have some bias if you apply them to some other range where you have of course, I mean, if your temperature is drifting away, then obviously this will not work. This is a very, very simple observation. So what do we do in Switzerland? So we have a Swiss AI initiative, which is a national initiative to train various foundation models. I'm one of the leads for the climate foundation model there. I'm also helping the language model, foundation model approach. And the idea, what we do is very simple. We have more data, more climate models, and more variables, and higher resolution. Right? So that's the current idea. We'll see if it flies. We basically train a model that is significantly larger in terms of all of these variables than the model we have trained, the models we have trained today, more than 4 trillion tokens. We actually have also a new tokenizer that is a bit more involved to describe. And then we do this at a kilometer scale, like the whole thing. Right? So that's the hope. And at the end, we could basically use this for all kinds of downstream in cooperation with Meteor Swiss. It's a global model, but you can then fine-tune it for specific local downstream approaches. So we also have other people who want to work with us, like Singapore, for example. They want to fine-tune this for Southeast Asia. And so it's a huge effort going on, and there is more to say about this, but not in this talk. But now the question is this enough? Because what does this training is actually more like a weather model again, because climate timescales are very different. Is more data and everything just addressing it? I'm not sure. So this is actually where I was a couple of days ago. Why am I showing you this? Just to, again, appreciate the complexity of our planet, and I'm sure you do. Here you see all these components. What I talked about for this part of the talk was simply the atmosphere. Like this is what's happening in the atmosphere, temperature, wind, and all of these things. But actually, if you look at climate timescales, you have cities, you have biogeochemistry on land, you have people wandering there, and you have all kinds of effects that are working in these timescales as we are looking at 100 years. Forests are dying, new forests are growing, and things like this. So this is not easily capturable in an AI model because we simply do not have the data for this.
I desperately want to say butterflies are flying, so.
That is true. That is true. That's true. And talking about nice things, so you may wonder, why do I have this person here? This is Giri from NVIDIA. So he's one of the architects of the Grace Hopper superchip. Who has heard about the Grace Hopper superchip? Nobody is too geeky. That's a too computer sciencey topic. But I want to tell you something about it. It's an interesting chip. So it's a chip that is one of NVIDIA's flagship products now. So most chips purchased from NVIDIA are not plain GPUs. They actually contain the CPU in the chip. Like the next version is called Grace Blackwell GB, and then there are multiple versions into the future. So you have a Hopper GPU on the left side, and you have a Grace CPU. It's called the Grace thing. And you can see the joke here. Grace Hopper is the actual Rear Admiral that this thing is named after. And you can also see the dilemma. They didn't update the GPU version, sorry, the CPU version, and now they have a Grace Blackwell, which is not the right name of Mrs. Blackwell. But that's the marketing issue NVIDIA has now. So let's look a little bit more at this chip. This is quite interesting for us because as we are running climate simulations, we have been mostly looking at running them on CPUs in the past, now porting all of them on GPUs. But I want to stipulate that we could actually run them on CPUs and GPUs at the same time. And we could run various components. Because at the end, all of the climate simulations, they live on very different scales. So they live on from millimeters to thousands of kilometers in spatial scales, but also from seconds, tens of seconds is the time stepping. You time step the atmosphere in a kilometer scale resolution to actually decades when you talk about forests developing. So forests are not very fast. Oceans changing major streams like the Gulf Stream, that is going to take years. That's not in the seconds. So if you set up an Earth system, full Earth system simulation, you need to consider all these things: atmosphere, land, vegetation, and ocean, including sea ice, because ice is melting. You have the albedo effect. It's a very, very complex system. Actually, the most complex system that I've ever seen in simulation. So, and you have biogeochemistry in the ocean and on the land. So in order to run a climate prediction, you cannot just run an atmosphere model. You need to consider the feedback loop that these forests are having. This is extremely important as far as I understand. So anything less than that is somehow not realistic in climate timescales, at least in a 100-year timescale. So we have to be careful with this. What we've been developing together with partners at the Max Planck Institute, and they have written most of that code with the German Climate Research Center, is a model, an Earth system simulation model that puts all of this together in a complicated toolbox. It's called the ICAN code, the icosahedral non-hydrostatic climate and weather model. So also they're not good at naming, I know. But this whole thing has 1 million lines of Fortran code. So it's a massive code base developed by hundreds of people over a very long time, I believe about a decade. And so I'm presenting now a piece of work that we've done together with the Max Planck Institute, with Daniel Klocke and Bernd Stevens, many partners, just to motivate this a little bit, that if we go for pure AI modeling of the atmosphere, that is not enough. We really need to consider all of these pieces. And I want to stipulate you thinking about this. How do we replace these pieces with something that is faster than what we do right now? Because right now we have these simulation pieces, but they're really handcrafted in some sense. I mean, the land component, the ocean component, and so this is not so simple. But let me tell you what we have right now. So we took all of these pieces and mapped them to this chip that I was talking about. So we are actually running the atmosphere, land, and vegetation on the Hopper GPU. So that's a GPU workload. But at the same time, while the GPU workload is running, we run the ocean and the biogeochemistry in the ocean on the CPU part. So on a heterogeneous system, we use 2 different types of processors to support this workload. Why do we do this? Well, many reasons, but the major reason is because the code is pretty old. So it hasn't been fully ported to GPUs. So much of that runs on OpenMP, some OpenMP on multi-core CPUs. And then much of that runs on OpenACC. And we're actually using a piece of software for the atmosphere component that we've been developing for a while. It's called DACE. And I'm sure some of you know about it because some of you here use it. But this was also in collaboration with Oli and others. But that's just the atmospheric part. So now this simulation that we set up is actually the largest global simulation that I know of. With all these components, it's a 1.25 kilometer resolution. It has 347 billion degrees of freedom just in the atmosphere, 2 billion in the land, 23 billion in the vegetation, and a 10-second time step to run the whole thing. On the ocean side, it's 86 billion and 326 billion pieces or degrees of freedom. These ocean biogeochemistry has all the variables, different algae forms and whatnot, and runs a 60-second time step. So now the funny thing with this is that you have a total of 780 billion FP64 variables to simulate. It's quite funny because it's actually more bits than the largest publicly announced AI model. We all think AI models are big. We all think like trillion parameter models. Well, a trillion parameter model is today stored in FP16 or FP8 even, which means 780 billion FP64 variables are significantly more data to work with. And it actually runs 30% faster than the fastest run. So we are at about 80 simulated days per day. Remember, the first goal was 1 simulated year per day. That's about 360. So we're not there yet. But we can run kilometer scale at about a third of that, if you have a quarter of that today. So that's quite nice. With this code base, with all of these components, this is not just an atmospheric simulation, right? It includes all of these components. So, and we basically get this ocean biogeochemistry for free in that setting. So that's quite nice. The unfortunate thing is it's also running on a very powerful computer. It's very expensive. But this is an example of what you can do with this. Is actually the ocean's interaction with the atmosphere, where you have certain in-gassing and out-gassing effects, or uptake and out-gassing effects that interact with, oh my God, that's not working, that interacts with storms here that are carrying the CO2 somewhere else. So this is quite an interesting thing to watch here. Unfortunately, through the Google Meet, it's not very fluent. But yeah, we can watch that offline. So that's what's going on. So now I've closed the simulation part. And here I'm leaving this with a mixed feeling in some sense, right? So we have all these AI models, they're great. They're already questionable for just the atmosphere. Like there are multiple problems with them. I believe we can solve those problems, but actually to get a real climate simulation, you would need to have the real climate prediction, the whole Earth model, like the Earth system model, like biogeochemistry and all of that stuff. So now let me go forward with the simulation data. As Chris said at the beginning, we spend a lot of time in my group worrying about how do we store that data? Because remember that 60 or what was it, 50 or 60 petabyte, that's very expensive. So, and what we chose to think about is compression. And so there's lossless compression and lossy compression. So we gave up on lossless compression. We're going to talk about lossy compression now. But we're going to talk about error-bounded lossy compression. So you can basically say, I'm willing to accept a 1% error in my data. And we guarantee that there is no more than 1% deviation at any grid point from the original date. It's a little bit more complicated, but it's the high level picture. So I will tell you about a scheme that does not support that arrow bounded yet. We'll be releasing the arrow bounded very, very soon. But what you do basically is you run many time steps in your simulation, and you store some of them. Like you time step every 10 seconds in your simulation if you run a large atmospheric simulation, but you store only every 15 minutes or every 6 hours. It depends on what resolution you want to store. By the way, for AI modeling, you may want to have a higher temporal resolution if you want to train AI models on that data, which even exacerbates the problem of data, because if you now time step more, well, you need to store even more data, which is very annoying. So then, very often in these analyses, when you ask a specific question on the data, you're asking specific question about specific locales. You're asking what is the weather over Seattle going to be in like 20 years, and you ignore the remainder of the planet. Like, so it's very often the case that when you go through this data, you look at very small slices of it. ECMWF even went so far that the interface to AR5 gives you a sliced interface. Like, you can only get small slices. You cannot download all of the data. We tried that. It did not really work. So then at the end, you get this multidimensional output data. And what we do, since we are AI people in my group, we had this idea that we should just train a network to faithfully reconstruct that original data. In other terms, is we take a neural network and we overfit it completely to this data. Like, there's no other training task. We just want this thing to not, please do not generalize. Please just reconstruct the data we feed it as a compression method. This actually is an interesting idea. It worked really well. So we get a 300 to 3000x compression. The only problem is, two problems, is we don't have a good arrow bound, because these neural networks, they don't give you any guarantees on their representational, I mean, they give you guarantees on capacity, but not guarantees on performance, representational performance. The second problem is, in order to compress anything, you now need to train a full deep neural network, which is extremely expensive. Like, your compression bandwidth is close to 0. The decompression bandwidth is very high, because it's just inference, you just run the thing. So it has lots of issues. At the time, we still believe that Fourier operators would be a good idea. We don't believe this anymore. I will tell you about it in a minute. But we could now talk about the details of the model. They're somewhat outdated, so let me not talk about this too much. But I guess you've got the high-level idea. We train this into a neural network to reconstruct, I guess, a compression. It's, by the way, very similar to Gaussian splatting. So if you're familiar with Gaussian splatting, that came later. Really cool technique. If you're not familiar with Gaussian splatting, look it up on the internet. It's awesome. It's going to revolutionize video gaming in so many different ways. So now we can look again at a case study. We have the reference climate field, which is uncompressed, like 1 times compression rate. We have our neural network field, which is 1,000 times compressed. And we have another compressor that is standard today, which scientists use, SC3, which gets you about 300x. And you can see, for this particular geopotential on this date, we get a very faithful representation at a higher compression rate than existing compression schemes. By the way, this SC3 we kind of drove to the extreme. They do not recommend to compress it with more than 100x. Like, so it looks good if you do 100x, but we wanted to show that we're actually better. So this is great. We get the general shape, nice. The only problem is, if you look at a specific hurricane, again, we like hurricanes, obviously, for studying reasons. And unfortunately, a bad hurricane again in the Americas. Our scheme basically turns this into a light wind, because we have Fourier operators. How do Fourier operators work? Well, you do essentially a Fourier decomposition of your data, and you cut off the high frequencies. If you cut off the high frequencies, you're going to cut off all your extreme events. So you get a very good faithful representation of the average image, which we have up here. Perfect compression, wonderful. But all of your extreme events are gone, which is very annoying. In the SC3 case, they get a very large bias everywhere else, but they still maintain the high gradients in the hurricane. I can exactly explain why, but again, I don't have enough time to explain this in great detail. So what we did was basically, well, we switched to a different technique. We say, oh, well, maybe Fourier operators are not a good idea because they're round, and we don't want round things. So this was actually kind of a cool thing. People developed wavelets. So wavelets can be edgy effects. And so we basically, instead of decomposing things into basis functions that are round, like sine and cosine, we decompose the image into basis functions that have edges. And this is what a wavelet function is, like the Haar wavelet, for example. Works similarly. We get 1,000 times compression rate here. You see no difference. Here's a similar scheme that was published in Nature that gets a 9x compression, but again, we are 100 times higher compression in this thing, so it's better. And now if you look at Hurricane Matthew, it's perfectly there. It's just because we changed the basis function of the learning. It's not round anymore. It's a very simple thing, works reasonably well, and is quite successful. So with that, I would like to conclude my talk now. We have work ongoing, by the way, on this compression, which we hopefully get finished very, very soon, where we have this arrow-bounded thing that I mentioned earlier. So this is all not arrow-bounded. We also have compression bandwidths of megabytes per second, which is not very high. But this neural network training is in the single bytes per second. So it's very heavy computationally. But we do have methods that now do megabytes per second on single cores, and that are very similar. They also use wavelet. They also use AI methods to go into this, but I don't have time to go much more into detail here. So let me just summarize the key points. So the first key point is climate simulation is extremely demanding. Okay, so keep that in mind. If you do it on a per pixel basis at a kilometer scale resolution. But most of these pixels are boring. If you look over the oceans, not much is happening over the ocean. Okay, I should be careful, like climate scientists in the world. Okay, but the ocean, yeah, for me, not much is happening. But then we can use AI techniques to accelerate pieces of this, like the diffusion process can be significantly accelerated, actually even getting you a higher quality at the end, which is quite interesting. Then the question is, what do we do with this prediction with AI models? I know you guys have wonderful work going on where you roll out AI weather models in climate timescales and show a lot of success. And this is great. So we're following and observing that work very carefully. But we still have all these little issues that I pointed out. How do we fix those? And then the problem is even more, and I don't have a summary slide for this here, is how do we solve the whole Earth system simulation? That is also not so clear. Atmosphere is fine, but the Earth system is a coupled system with many, many effects. And then we have this compression work, which I believe is absolutely necessary to do any of this, because nobody will have enough memory to store the data. Even if you run an AI-based forecast, you still need to generate all this data. And so that's the thing. In general, what we want to achieve actually as kind of a stretch goal is we want to get all of era 5, and many of you know that data set. It's about 5 to 6 petabyte, depending on how you count, of data. We want to get it on your USB drive. Because right now it's a pain to work with era 5. It's just a pain to download it. But it's also a pain to work with it because it's so large. But if you can compress it without significant errors 1,000 times, then it fits on your USB drive. Then you can do it on your laptop, which would be cool because that's the whole history of our planet as accurately as we have it on your USB drive. And then if we have a lot of opportunities for joint work, and so join us in Zurich. Zurich is a beautiful city, and so the weather here is competitive though, but yeah, Zurich is a beautiful city. Thank you very much, and I'm open for questions and discussions.